facts and 2 assumptions. The facts are there have been over 60,000 papers using novo transcriptome assembly since 2011 when the Trinity paper was first published, and that they have been practical because it's expensive to build whole genomes, at least up until recently, and that for people who have very large genomes, there just isn't another option available at the moment. The assumptions are unstated and they are always there. One, that your assembly is an unbiased representation of the expressed transcriptome, and that the expression estimates are noisy, but hopefully unbiased. We had 2 questions with respect to these assumptions. Number 1, are they robust? And secondly, do violations distort evolutionary inferences? And so we pulled out a bunch of data from model organisms with the idea of comparing mapping to reference genome and annotation-based approaches to novo transcriptome assemblies. Most of the analyses I've done today all involve MUS and Trinity. We've done similar things with Shannon and Binpacker as well for most analyses, and we did some other ancillary analyses with fly and clod frog and pufferfish. Our dark killer number 1 is that there are pervasive genotyping errors. If you want to do population genetics with assemblies, be forewarned. We can compare genotypes from the 2 methods by doing the standard GATK best practices for mapping to a reference genome with RNA-seq, calling variants with GATK, and popping out a BCF file. We can similarly use super transcripts, which are basically kind of like the compression of all the overlapping sequences into a continuous sequence that represents sort of the genic level continuous sequence from a transcriptome assembly. And then we kind of compare those genotypes. And we don't just compare genotypes. If one is invariant because the alternative allele is present and fixed, and it's in the actual reference sequence, we look at the overlapping sequences, and so we map with GMAP the actual super transcript so we can get a point-by-point, position-by-position homology to identify whether the allele sets we identify match. And guess what? They don't in a lot of cases. The 2 samples on the left are inbred MUS lines. MDC is the dendritic cell data set from the very first paper, the Trinity paper. The others are French, German, Iranian, and Kazakhstan pools from wild MUS. And so rates are typically approaching 40% in the wild samples, and they can be much higher in inbred lines, right? So basically, the set of alleles in the 2 methods do not match a good part of the time. We also have serious problems with false negatives and false positives. False negative rates in the wild samples are well over 20%, or over 20%, and the inbred lines are much higher. I should point out that this includes cases where super transcripts were not assembled over variant positions, right? This is going to be a key thing, that we're not assembling over polymorphic sites in the genome and may bias our estimates. But if we still look at these rates of false negatives, and I should say, take a step back, in these cases with classification and error rates, we're considering true positives as heterozygous positions when we map to reference. Okay? So if we exclude sites where there is no super transcript overlapping the genome, we still have relatively high false positive rates, or about a little over 10% in the wild pools, and still very high, over 30%, over 50% in the inbred lines. We also have false positive rates. That is, we're calling heterozygous in positions where they don't belong. And then recall is just a flip of false negative rates, and I put this here because these recall rates are very similar to those found by Nadia Davidson and colleagues who developed the Corset clustering algorithm. This came out in Genome Biology a couple of years ago. And this was the genome in a bottle data, so this was kind of like, we're wildly off with respect to this metric. One kind of evolutionary consequence, consequence for estimation with respect to an evolutionary process is that diversity is underestimated. If we compare heterozygosity between the 2 methods, what we see is there is a consistent, if small, underestimation of heterozygosity in the wild samples, but not really in the inbred samples. We were curious why this might be. And so one possibility might be we might have reduced power to call variants or heterozygous positions if we have reduced depth of coverage at those sites. And so this is a plot of the y-axis of the depth of coverage at supertranscript positions, and the x-axis is mapped to reference, right? And the blue dotted line is basically the fit if we exclude sites where there's no supertranscript overlap. And we see only a slight reduction in the trend overall in coverage. And so at these positions, this suggests that this is probably not the major effect driving the problem. But if the yellow dotted line includes those sites that are missing, we say if there's nothing assembled there, coverage is 0. So this is indicative that this loss of assembly over variable positions is probably the problem. What are the implications here? Number 1, your biggest problems are going to reveal things like allele-specific expression, EQTL analyses, because you're trying to get specific variants to tag, heterozygous variants. You can figure out whether it belongs to an allele or a specific variant belongs to a phenotype, or it tags that phenotype, or a locus that basically is causative for that phenotype. Secondly, as I've already indicated with these diversity estimates, is that you're compressing your diversity estimates towards 0, right? So if you compare a bunch of assemblies, there may be an actual signal of diversity that affects this due to like history or whatnot, but the thing is, it will be harder to identify that process given this sort of negative bias. Probably also problematic, selection scans, population structure inference, anything where you require like an accurate estimate of the site frequency spectrum is potentially problematic. And the big picture here is that errors decrease our signal to noise ratio. And with particular respect to false negatives, you lose power. Our second dark tale of the day is about expression bias and noise. So in these plots, what we've done is we've basically blatted contigs to reference transcripts, so we have a very good idea where these belong, right? And so we can assign things to a transcript, and then we can assign it to a reference gene. The first take home here, people often use a single contig. The best hit contig or the one whose contig is a proxy for expression for a transcript. Look at what these correlations are. These are for basically the x-axis is expression for count per million or transcript per million with mapping to reference, and the y-axis for the Trinity assembly. And they're a cloud. And there we see the trend lines are basically showing the mean trend, and there's bias in both directions with CPM, and pretty bad bias, positive bias, low expression with TPM. Now, so don't do that. Don't take one contig and try to use it as a proxy for a gene or a transcript. Aggregating, of course, helps at the gene level. If we take all these contigs, if we can reliably put them in a bin that belongs to one gene, we can aggregate expression across them. Counts per million looks pretty good. There still is positive bias, low expression levels. There is a bit of noise about that line too, but TPM in particular shows this sort of like rather large bias, this cloud at low expression levels, and it kind of persists until slightly higher expression levels as well. But again, a lot of noise. What might the cause of this be? Our intuition here was it was about misestimating effective length, which is the number of positions you can map a library fragment to a gene model, right? Which is basically a feature length minus the mean fragment size of your library plus 1. In the ideal world, you have a transcript, you fully reconstruct it, and let's say your library size, your fragment size, your mean size is 250 bases. The effective length is 751 bases. If you break that into 2 pieces without missing anything, your effective length is 502, and so on and so on. The more you fragment, the more you miss, that effective length goes down. The proof of principle here is that we can plot log-fold change of an expression metric between the de novo estimate versus the map to reference over a log-fold change, if you will, on effective length estimates. And what we see, there's a trend. As your effective length differences decrease, the difference in your expression estimates between the 2 methods decreases. It's worse for TPM, and one of the take-homes here is that exporting TPMs for things like phylogenetic comparative methods may be problematic because there is bias simply due to this effective length difference between samples. We propose a novel correction method based upon this problem, and it is sort of very tailored for transcriptome assemblies. We set one set of features as a truth, and we adjust effective lengths to that based upon the difference or the disparity in effective length for a set of contigs that maps to a specific gene, or a set of 2 sets of contigs from 2 assemblies that actually, or 2 methods that belong to a certain gene. And this is simply, we account for 2 things. The actual length difference, right? If you only have one fragment of an overall gene, by definition, your effective length and your length are different. And then the effective length difference, which is basically which is mostly affected by how fragmented, conditional on the length you actually recover. And so we multiply by these 2 scalars. The first one here, that's what I want to do. The first scalar accounts for this difference in gene length, and the second accounts for the true length you've recovered. And this also keeps the data in count scale, which is kind of nice because like things like limit take CPM to 0. And hey, bias is reduced. It may be hard to see because the correlation only goes up slightly. These are Spearman rank correlations. But the x-axes or the y-axes are the same, and so you see they're actually putting a bit of compression of this noise about the line. But perhaps we don't care, right? Someone might say, if all the biases are in the same direction, why do I have to worry? Because they'll all basically average out in the end when we compare samples or paired assemblies. And what we can do is we can take 2 different samples, we can look at the log-fold change between methods for one and compare it to the other. And if all is nice, if there's no bias, well, we would expect some strong correlation between the 2, right? And so on the y-axis here, we have the log-fold change between methods de novo versus map to reference for the German sample, and one on the x-axis is the French sample. And guess what? There's a reasonably strong correlation with quite a bit of noise about the line. But we would argue that considerable bias remains. And we want to make sure that it doesn't. And so we're going to define something called a bias effect size, which is how different the logical change estimates are from the macro reference when using the novo transcriptome assembly, right? Like, is there some subset genes that show wide variation in the directions of bias between samples that might impact differential expression? This is the math. If you want to look at it, I don't have time to talk about how it works, but it's some simple algebraic rearrangements. And if we plot these for the various metrics, we see that sometimes 2 up to 5% of genes may have a tenfold difference between samples in the direction of bias, right? So a number of 10 means that one method, the de novo method, produces a difference between samples that is 10 times that of using macro reference, right? And this is like in the arena of where your false positive rate is. So you're talking about possibly confusing true signals with false signals. But the rescaling helps a bit. This is a naive correction. It's possible we could do some better things that are more sophisticated in the future. We might be working on that. One final thing I want to talk about is what I'm calling the filtering trade-off, right? What I've shown you so far are on unfiltered assemblies. But in the real world, we're mapping to uniref. If we can't annotate, it doesn't make any sense. And blatting mus to mus is ideal, right? So most people filter out lowly expressed contigs and they dump anything that's not annotated. And if we dump all that stuff, we only focus on protein coding genes, their correlations are much better. And guess what? TPM looks better too, right? But there is one elephant in the room with this, which is that if you have protein coding genes, and they're there and present based on what we know, and we've done this filtering on the contigs, we've annotated them, right? They're protein coding, we know they are. We will lose 20% of protein coding genes by requiring that we have a blast hit to a database and we filter out lowly expressed contigs. This is the histogram of expression levels for those genes that do this. Okay? And so a lot of TPMs of 100 or 1,000, a lot of stuff that might be functionally important to you. The take-homes here, inference based on genotyping from these assemblies is problematic. It might be mitigated with better clustering than supertranscripts or better ways of sort of like condensing your transcriptome, but it's hard to mitigate false negatives. Secondly, there is bias in expression levels. TPM is particularly bad. Aggregate to gene level helps, perhaps a surprise there. And correcting for effective length can help these disparities. This is potentially useful for comparing expression estimates across different transcriptomes.